Okay, so let's go ahead and start. So now we're going to talk about the chi-squared distribution. For chi-squares, you're going to use qualitative data, and remember that's data in categories. You wouldn't use this for quantitative data, and in a few minutes you'll see why. So first of all, let's look at the notation for chi-squared distribution. If you see this X right here that kind of looks fancy, it's kind of a fancy X as I call it. Actually what that is that's the letter chi in the Greek alphabet. And you know, as you've been going through this semester, you've seen that we use Greek letters a lot. So for this one, for the notation for chi-squared, it's chi is equivalent to chi squared with the degrees of freedom, where df is degrees of freedom, which depends on how your chi-square is being used. So if you want to practice calculating chi-square probabilities, use df, the degrees of freedom, which is your number of categories minus 1. So for chi-square distributions, the population mean is the degrees of freedom, and the population standard deviation is the square root of 2 times the degrees of freedom. The random variable is just shown as chi-squared. So there's some rules for chi-squared. The curve is non-symmetric and skewed to the right. Number 2, there's a different chi-square curve for each degrees of freedom. And they do look extremely different. Like if you had one with the degrees of freedom of 4 compared to the degrees of freedom of 100, they're going to look different each time. The test statistic for any test is always greater than or equal to 0. When your degrees of freedom are greater than 90, the chi-squared curve approximates the normal distribution. Do you remember we talked about that before? And that's that really pretty bell-shaped curve. So as you get above 90 for your degrees of freedom, it starts taking on that normal shape, which is wonderful because, as you remember in the past, there's so much we can do with that normal distribution. It helps us to look at data in huge pockets and make assumptions or educated guesses on the areas and the percentages. So if you had a chi-squared where your degrees of freedom were 1,000, the mean would be 1,000 and the standard deviation would be 44.7. And therefore, we can use the normal distribution to approximate what it's going to look like. Number 5, the mean is located just to the right of the peak. And remember, we said it was skewed, so that makes sense. So the first thing we're going to do is we're going to do the goodness of fit test. And in this type of hypothesis test, you're determining whether the data fits in a particular distribution or not. For example, you may suspect you run known data fit a binomial distribution. And a binomial distribution is it's almost like a yes or no question. Is this going to happen? Yes or no. So you use a chi-squared test, meaning the distribution for the hypothesis test is chi-squared, to determine if there's a fit or not. The null and the alternative hypothesis for this test may be written in sentences or may be stated as equations or equalities. So the test statistic for goodness of fit test is sigma k, where the observed minus the expected squared over the expected. And k is the number of different data cells or categories. I know that looks really tricky. Don't worry about this. I'm going to walk you through this step by step. And then in the next video, I'm going to show you how to use a website that does this for you and does it beautifully well. Because some of your calculators might not have it on there, and I don't want you to struggle. I don't want the math to be the issue. I just want you to understand the process and be able to tell me the results. So the observed values are the actual data values, and the expected values are the values you would expect to get if the null hypothesis were true. The expected value for each cell needs to be at least 5 in order to use this test. And that is really important in the real world. If you don't have 5 in each category, your results are skewed. And when I was in grad school, I had to worry about this all the time. So I'm really cautious now, but for what you're doing in this intro-level stats class, you don't need to worry about that. So the number of degrees of freedom, and I said this before, is degrees of freedom equal number of categories minus 1. I keep saying that because sometimes people get confused and use the sample size. So the goodness of fit test is always right-tailed. If the observed values and the corresponding expected values are not close to one another, then the test statistic could get very large and will way out in the right tail of the chi-square curve. All right, so let's try an example. Again, I don't want you to do this by hand, but I'm going to show you the process so it makes sense. Employers want to know which days of the week employees are absent in the 5-day work week. Many employers would like to believe that employees are absent equally during the week. Suppose a random sample of 60 managers were asked on whether the days of the week they had the highest number of employee absences. The results were distributed in Table 11.6. For the population of employees, do the days for the highest number of absences occur equally frequencies during the 5-day work week? Tested a 5% significance level. Okay, so what they're saying here is there is no difference in the amount of absences during the week between Monday, Tuesday, Wednesday, Thursday, Friday. They're all the same. So people are going to be out the same amount. So here is the observed data. So the number of absences on Monday was 15, Tuesday was 12, Wednesday was 9, Thursday was 9, and Friday was 15. So now we're seeing Monday and Friday are pretty high. But don't make that assumption, because what we're doing is we kind of are taking the average, of all this data to see if they're really equal. All right, let's talk about our hypothesis. To me, chi-squared have the easiest hypotheses to make. So the null is the absent days occur with equal frequencies. That is, they have a uniform distribution. And a uniform distribution basically would almost look like a rectangle across the axes. Because what it means is Monday will occur at the same frequency as Tuesday, Wednesday, Thursday, Friday. Your alternative is the absent days occur with unequal frequencies. That is, they do not fit a uniform distribution. It's that easy. Or I could have said that the percentage of Monday equals the percentage of Tuesday equals the percentage of Wednesday, the percentage of Thursday, the percentage of Friday. It just depends on what's comfortable for you to write. All right, so let's solve. All right, so the first thing I need to do is find my expected. And I'm going to do this in a table. I did this in Excel, but I popped it up here just so you can see it. Remember, I don't want you doing this by hand. I just want you to understand the theory behind it. Okay, so here's my observed. To get my expected, I added all my observed up to get 60, and then I divided by 5. Where did that 5 come by? That's the number of categories. So if I do 60 divided by 5, I get 12. So my expected for each category is 12. So now I need to subtract my observed from my expected. So all I did for Monday was took 15 minus 12 equals 3. Tuesday, 12 minus 12 equals 0. Wednesday, 9 minus 12 equals negative 3. It is okay to get negative numbers. It's fine. Don't worry about it. So, okay. So the next step, and I know you're like, whoa, why are we doing all this work? If you had to do it by hand, and they used to do it by hand, many moons ago when I was an undergrad, I had to do this by hand. We're going to square the observed minus expected. Why are we doing that? Because we want to get rid of those negative numbers. Remember I said before, your test statistic is going to be 0 or greater. This is why. All right, so all I do is square it. So for here, I just squared 3 on Monday to get 9. 0, I put it here. 0 squared is 0. Negative 3 squared is 9. Remember, when you square a negative, what happens? It becomes a positive. Okay, so that's observed minus expected squared. So now I'm going to do it. I've got to take my observed minus my expected and divide by my expected. See, I told you don't want to do this by hand. So 9 divided by 12, 0.75. 0 divided by 12 is 0. 9 divided by 12 is 0.75. So you see what's happening now is I'm starting to get my test statistic. And the next step is to add them all together. And if you see here, here's the last part of that table. And then I just came over here and added it together. So the test statistic is 3. So my answer, my test statistic is 3. My degrees of freedom is 4. To get the p-value, there is a way to get it in your calculator, and I'm showing you right here how to do it. But again, I really don't want you using the calculator for this. In the next video, I'm going to show you how to go to a website. You put your data in, and it just gives it right back to you. So you go to second distribution, you scroll down to chi-squared CDF, and you hit enter. So then I'm going to enter 3, which is my test statistic. Positive infinity. Why am I doing positive infinity? Because of the chi-square distribution. Comma 4, which is my degrees of freedom, and then I hit enter. And then I get my p-value is 0.5576. So remember I said before, I'm going to test this at a 5% level of significance. So I convert that to a decimal and I compare 0.5578. Is that greater than my alpha? Which it is. Remember, if your P is greater than your alpha, you fail to reject your null, and that's what I'm doing. I'm not going to reject my null. I'm going to keep it. What does that mean, though? So if we decide not to reject the null, it means we found the null hypothesis to be true. So we need to conclude it properly. At the 5% level of significance, there is not sufficient evidence to conclude that the absent days do not occur with equal frequencies. What? That's really confusing. So what we did is we put in here, we stated the level of significance, and since we failed to reject the null, we based our conclusion on the alternative hypothesis. I know it's crazy, but in statistics, that's what they do, because you're not really testing your null, you're testing your alternative. So again, let me tell you what we did. So basically we said, yeah, we're keeping the null. So what does that mean in everyday speak? It means, remember, even when we saw Monday and Wednesday, that they were really high. But when you looked at the, I think it was Wednesday, Thursday, where they were 9, that brought the number down. Because remember, basically what we're doing is we're kind of finding the average days, the expected, which was 12. And 12 was really in the middle of that data. So saying that then, that meant that for these 60 managers, there's really no difference in the number of averages. So when you conclude it in statistical speak, as we call it, at the 5% level of significance, there is not sufficient evidence to conclude absent days did not occur with equal frequencies. So all I'm saying is there is not sufficient evidence to support the alternative hypothesis. That's all I'm doing. And I know it's kind of confusing. And over time, it'll start to make sense. Okay. Well, sometimes you're going to get chi-squared where they want different percentages based on the different categories. So to determine the expected values, you will always get your sample size. Remember, you add all the observed values. And based on the particular category's percentages, you will cover the percentage to a decimal and multiply the decimal by the sample size. So for example, for the last example, the sample size was 60. What if the manager believes the absences occur 40% on Monday? So all I do is I convert this 40% to a decimal and I multiply it by 60, which I'd get 24 is the expected number of days for Mondays. Again, we're going to use a website to help us because I don't want you doing this by hand. So that was the lecture video. So the next one will be on using the website. I hope this helped.